I'm very, okay, click on continue. Okay, I'm very happy meeting with our alumni today. I'm one of the sustainability specialists in our campus, and today I'll talk about my research regarding sustainable energy. Today, I'll talk about the general scope of sustainability research, and then I will focus on my research activities in the field of solar energy. Next, I will present some key research questions from my studies, and finally, I wanted to talk about my ongoing projects, proposals, and some collaborations in and out of our campus. Well, I do sustainability research, and sustainability research is about making a trade-off analysis between the alternative products, processes, or any engineered systems to use our limited sources more responsibly in order to maintain the quality of life for future generation. In engineering world, we are familiar with the trade-off analysis to achieve low-cost solutions. However, in sustainable engineering fields, approaches in addition to economy, trade-off analysis with the focus of environment and society are required. The tool to conduct the sustainability research is called life cycle assessment. And so far, I have applied this form of analysis to analyze water management systems, such as stormwater harvesting systems for green buildings. I have also applied these analyses in collaborations with industry in designing manufacturing of wide range of products from construction materials to agro-industrial waste. More specifically, in photovoltaic, uh, so I, I also applied the tool in production of energy-related work, starting from photovoltaic research to biofuel generation systems. And more specifically, in photovoltaics, my research focused on the production, design, and recycling of emerging and commercial PV materials and minimizing their toxic impact. So this is the general scope of my research on related sustainability. So from now on, I wanted to go through go through a little bit solar energy related research a little bit. So I'd like to start a little bit background information here, but I wanted to make a quick start here. And here you see the cost of electricity in the United States that can be supplied from renewable and conventional technologies. Now let's blur the expensive technologies, energy sources, and focus on the most cost-effective three technologies that can generate electricity, which are wind and two solar technologies here. So we see that unlike wind at the bottom here, um, solar is capable of providing energy with a narrow cost range, which emphasize the potential of photovoltaics in energy market. And my research efforts, I think, as well as the entire solar community in industrial or research scale, is also aimed towards reducing this cost further. So, how can we achieve this? How can we make the cost of electricity supplied from solar more cost effective? So let's take a look in this piece of solar panel. So this is called a solar cell, and we manufacture these cells to generate electricity, converting sunlight into solar power. And there are actually two things we could do to reduce the cost of electricity from solar. One, we could improve the current solar technologies by replacing their material content with low-cost materials or advancing their manufacturing techniques. Second, we can explore new designs or concepts that can increase the power conversion efficiencies for PV devices. So creating more power from the unit area, basically. Well, some emerging technologies that I'm going to talk today can achieve both of these. So they can cut from the expenses and then they can also increase the power generation per unit area. So they are helping the more economically sustainable energy from solar fields. Um, so I wanted to continue a little bit giving more background information about solar technology. So here we see the same solar um, PV again, PV cell again. So now let's look into the cross-section view of this field. So the cross-sectional thickness of the solar material is about 1 millimeter. And a closer look at the solar material structure shows that the module is actually made up with 5 thin layers. So each layer has a distinctive purpose in this structure. And there's an absorber material in the middle. It is covered by electron and hole transport layers, and there are front and back contacts on the surfaces. As sunlight strikes to this semiconductor material, it excites the electron in the absorber layer, and an atomic scale movement or flow starts between the electron transport layer, between the front and back contact of this PV cell by the help of the electron and hole transport layer. So this flow is called direct current, DC, which is converted to alternative current, AC, within an electricity inverter. So there are alternative materials to make each of these layers here. But the absorber material is the most important layer because it classifies the type of the technology. So here in this picture, we see the most common absorber material used in solar market, and that material is called silicon. So it's silicon absorber material, or crystalline silicon, or monocrystalline or polycrystalline silicon material is used as an absorber material here. Well, so let's look into what kind of technologies available based on their absorbers. So here in the commercial side of PVs, and then there are those emerging PV technologies which are still under or in lab scale still, or not very common in the PV market as for now. So regarding the commercial PV technologies, there are wafer-based technologies and thin film-based technologies. So wafer-based technologies contains this polycrystalline silicon and monocrystalline silicons, and according to the thin film category, we have amorphous silicon material, cadmium telluride types of PVs, and copper indium gallium selenide, which is called CIGS or CIS types of thin films are available. So what do we have in the emerging side? There is Perovskite technology. So some carbon nanotubes are also used as an absorber material. Quantum dot technology as a nanomaterial is also used. Organic polymer PV technologies and inorganic based copper zinc tin selenide or CZTS types of PV technologies are available. So what do we know about overall view of these technologies? Well, these commercial PV technologies, they are efficient, they are a little bit costly, and some of those thin film technologies, especially tellurium in CATL or gallium and indium in CIGS technologies, contains certain rare elements. So what we know about the emerging PV technologies again in general, so they are mainly based on earth-abundant materials. They are less costly, but they have some instability issues that makes them still in research scale now. So this is the general scope of PV technologies. So now I wanted to move into some key research questions from my research. Well, the most prominent member of emerging photovoltaics is perovskite PV, and the immense interest from the solar community is a testament on it. So these are the numbers of publication on perovskite PVs since their discovery in 2009. So which shows really the level of interest from the scientific community. So within 10 years period, there are many perovskite PV related publication has been made. But why is that? So what makes perovskite PV so popular? So let's look into these two figures now. On the left side, you see that yellow colored chemical. And on the right side, you see the crystal structure of perovskite. So both of them, they are the perovskite material, that absorber material we have in this new PV technology. So metal ammonium are on the corners of this crystal structure, and there are some halogens, which could be iodine, bromine, or chlorine, are on the surfaces, and there is that lead ion in the middle of the structure part. So as you see here, none of these materials are really expensive or rare, so these are all earth-abundant materials. And on the left side of the figure again, so this organic organometal or organic inorganic composition is a solution. So that makes it printable. So being printable and having low-cost materials. So these are two important parameters that we really care when we develop a new technology. And I wanted to add on top of this now. So here you see the National Renewable Energy Laboratories Best Research Cell Efficiency Chart. So this includes all types of technologies that exist today, and it shows how cell efficiencies evolve with time and who break the efficiency records. Every technology here has its own color, and the light purple, this part, depicts the tandem cells, so meaning that more than one PV panels are stacked onto each other. So these are extremely expensive materials since there are multiple layers available in these PV technologies, and they are mainly used for space missions, so to cover the surfaces of the spacecraft, basically. So now I wanted to simplify this graph a little bit. I wanted to compare perovskite PV technologies with other emerging PVs. So as you see, the efficiency of perovskite is more than 25% today. And it is almost doubling one of the best, not doubling, but it's very high compared to other emerging PV technologies. And their discoveries, again, very recent, starting from 2009. So now let's compare this perovskite PVs with the commercially available PV technologies. And when we look at this efficiencies again, it is very similar to crystalline silicon PV's efficiency limit records, around 25, and it's a little bit higher compared to those CAD-TEL and CIGS PV panels. So what does this graph say is actually? So these commercially available technologies are in the market for several decades, since Silicon is from 1970s. CATL, CIGS, they start 1990s or in the beginning of 2000, some of them, some specific technologies. So this shows really the potential of perovskite as a game changer in the PV market. So while perovskites are showing a potential to enter the PV market, the question comes to mind is, will they be more environmentally friendly than the commercial PV technologies? So would that really make sense for us to switch from conventional PVs to these new PV technologies from environmental point of view? So this is one of the study from my group. So in this study, we applied an LCA, but first we defined what kind of perovskite that solar industry may want to have in the market. So we have to look into from two perspectives. From the manufacturing perspective for PV manufacturers, PV photovoltaic, or from the materials perspective, again for the manufacturers. So they need to find those low-cost materials. So in this paper, we went through a rigorous methodology to address all these aspects. First, we consider all type of alternative materials that are commonly used in perovskite PV structure. Then we made a cost basis elimination, and here we defined the cost in both terms of material and processing cost. So as a top contact layer material, we identified fluorine doped tin oxide, or FTO, could be the best alternative. For an electron transport layer, tin oxide could be the low cost and low processing material, low processing cost material. As an absorber material, we identified methyl ammonium, lead iodine could be the best one. And for a whole transport layer, copper thiocyanate, an inorganic material, wholly inorganic material, could be better compared to copper iodine or nickel oxide and those organic materials. And as a back contact materials, we identified molybdenum oxide mixed with aluminum could be the again the best alternative from cost perspectives. Well, then we'll look into the different manufacturing techniques here. Perovskite can be deposited on the glass layer by vapor-based methods or solution-based methods. So in the vapor-based methods, vacuums are being used, and solution-based methods, there are spin coating, spray deposition, or dip coating methods are available. So for the vacuum-based deposition, again, this requires lots of electricity to create those vacuum conditions. So it's very similar to the conditions that we have in other thin film PV technologies. So if you wanted to move towards a greener production, then we need to get rid of those energy involved manufacturing techniques. So we remove that. And regarding the solution-based methods, so spin coating, for example, gives great results in lab scales. When we work on cell size, maybe like 1 inch by 1 inch. So this size, this is great. It can spin it. But in industrial scale, when we have 1 meter by 1 meter PV panels, or 1 meter by 2 meter PV panels, like First Solar's PV modules, it wouldn't be very efficient. So industry wouldn't like that. So we remove that. So deep coating methods, again, it is again a good method in lab scale conditions, but in a large scale production, you're gonna waste a lot of materials, you're gonna contaminate some of them, then you have to recycle your chemicals again, and then this would be, again, wouldn't be very practical from industrial perspective. So we have chosen spray deposition techniques for perovskite manufacturing. Spraying versus printing techniques, they are basically the same from environmental impact assessment perspective. Okay, so once we identified our photovoltaic modules, then we need to create the module, the LCA models in our software. So my team used Gabi software, and we have purchased Ecoinvent database embedded with this software. Then we have to define the scope of the study. So that means for any LCA study needs to contain certain phases. So it's starting from the mining step or material extraction step, and then the second step is manufacturing step, and then the use or operation phase, and then end of life phase. And between each of those phases, there will be some transportation. So what we did in the study, end of life phase, since these PV systems are not in the market, we have little idea about what happened in their end of life. So there are lots of uncertainty at this point. So we removed that phase from our study. So for the use phase, we are not expecting a lot of environmental impacts from the use phase. It is because, again, the main problem we have during the use phase of PV panels are soiling. So which PV panels needs to be cleaned by time to time to just get rid of the cover of soil during the use phase. But these are not like huge impacts. And then for the transportation, so again, we have little idea when and where we're gonna manufacture these PV panels, and then where we're gonna deploy them. So we remove those phases, which could be very comparable to other PV technologies. So that uncertainty can apply in comparison of other PV technologies. So we mainly focused on mining and PV manufacturing phases in this study. So when we talk about life cycle environmental impacts, there are many environmental impact categories. So it's starting from total freshwater consumption, marine eutrophication, primary energy demand, human toxicity, ecotoxicity, human toxicity, cancer, human toxicity, non-cancer, acidification. So these are all important impact categories that we have. And what we know, for each of these impact categories here, the units are different. So we also know that our purpose by introducing a new technology into the market is making a more sustainable decision. So we wanted to see if new technology is better or not than the conventionally available technology. So for this study, to understand our results better, we first apply all of these assessment for the market dominant PV technology, which was the crystalline silicon that I mentioned you from the earlier slides. So we calculated all of these different environmental impact categories for crystalline silicon. Then to simplify our results and then get a little bit larger audience for our research, we normalize them, kind of based an internal normalization based on crystalline silicon impacts, and then consider all of them as one impact. So we ended up with a unitless number, 9 here, since we have 9 impact category. So here the discussion would be for perovskite PV technology, would it be higher or lower than 9? If it is higher than 9, then we're gonna say, well, decision makers, there are those problems evolved with perovskite PV technology. So either fix those at this point or not to go with this perovskite uh, technology to come up with a, a better technology. So it could be cheaper, but it has these many of problems. So that was basically the idea of the study. And here are our results. So for crystalline silicon, again, the total impacts, normalized impacts are 9 points. And for perovskite, we have a chance to reduce our impacts by more than 30 times, 40 times. So it is 0.6. And look at other thin film technologies such as CAD-PAL and CIGS. They are about 6 impact range. Now, again, our perovskite technology is 10 times more environmentally friendly compared to other thin film technologies. So there is huge potential for perovskite PV technologies to be a greener solar energy source. So that was for the environmental impact assessment part for the general comments about the PV technology. But we have one more question here. Remember, we have that lead material in the middle of the crystal structure. So we wanted to understand how that some toxic metals are impacting our environment, especially from the toxicity perspective. So the question here is, do the emissions because of the instability of materials cause the toxic concerns in use phase of emerging PV? So that's our question. So I wanted to expand this instability problem a little bit here. So instability is a technical problem basically. So this is that crystal structure again. So what happened when the structure exposed to heat, light, or water? It decomposes to methyl ammonium iodine and lead iodine. So lead iodine is a very unstable material, so you ended up with an highly soluble lead material in the sun. So that instability is also an environmental problem. How is that? So let's say you have this solar panel, perovskite solar panel in your garden, and then it exposed to heat, light, water every day maybe. And then let's say you have a little crack on the surface of your PV panel. In this case, you'll end up with releasing some of the toxic metals into your soil, let's say. Or it may end up with your water through the rainwater harvesting system or the stormwater management system. These are all the possibilities. So we wanted to understand if we have a problem here from the toxicity perspective. Okay. So in this case, from the scope of study, we wanted to compare metal extraction and use phase related toxic impact. So that would give a better idea for us to understand how use phase is important for solar materials. So those PV materials that we may have in emerging thin film technologies could be cadmium selenide, copper thiocyanate, lead iodine, lead sulfate, nickel oxide, tin oxide, tin selenide, or zinc oxide. So these are the materials, and we come up with some models that we can copy from the model from the literature that contains them in different structure, emerging PVs. So again, we created all of these models using our software, Gabi software, and then look into the impact of the metal toxicity here. So we have to develop a model based on Noyce-Whitney equation here. And so here are results. So the first part of the question can be compared with how are the emissions from emerging PVs comparable with coal? So when these perovskite PV technologies are emerge, then some of the coal guys come and say, hey, you guys have lead, we also have lead, and this is like, well, that we are also toxic, but you are getting lots of funding. So what is that problem? So this is what we see in production of 1 megawatt hour of electricity from coal-fired power plant versus emerging PV technologies. So none of those metals that we end up in a worst case scenario. That worst case is basically the cracking. So we consider all this worst case scenarios. Still, these are not, none of them are comparable. It makes a little bit copper related impacts, but not again the lead related impacts here. So it is comparable compared to coal. So from mining phase, these are the impacts are even not visible. From the use phase impacts, we see a little bit, but again, these are insignificant level compared to coal-fired power plant. So this part answered the questions about the toxicity of these emerging PV technologies, especially the ones involving perovskite. So now I wanted to continue a little bit with some new types of designs, so some tandem devices. So to make PV be capable of more capable of feasible PV technology, we could increase our efficiencies more. So it is the efficiency limit that applies for single layer PV panels are about 30% or 33% is the limit, the efficiency limit. In the module level, it drops a little bit more. But there is that possibility when you have two stack of PV panels, and then we're gonna call them two terminal tandems, then your efficiency limit increases from 33% to 42%, around that range. So that increase means a lower cost basically. So industry really like this idea. And actually that's the reason at this point we have only one company, Oxford PV from Europe, started with perovskite technology on the top of their silicon technology. So they think it would make more sense from environment economic perspective to start this technology. Okay, so what happens with two terminal tandems that has perovskite on their top? So here is one PV cell having 30% or around 30% efficiency limit. And then you bring a low band gap and high band gap PV technologies and merging them. And you would need a, a junction layer here to, to connect these two types of PVs. And then you'll have a higher efficiency limit. Okay. So again, these are looking feasible from economic perspective, but we don't know their environmental impacts at this point. So we look into that impacts. Again, we made a literature review and come up with some good designs from the literature, and then look into their efficiencies as well. We define all types of layers using these PVs, and then create our environmental model again. And then here's the question. Will tandem cells have lower environmental impacts than two constituent single junction devices? So does that mean should we have two separate PV cells, or should we have a single tandem cells, which is more environmentally friendly? Here are results. So the left side is for the tandems, and the right side of each of these graphs are for the separate single cells. So in separate single cells, you have 7% to 30% more environmental impacts. And the main reason here is due to the additional use of glass. So all of these thin film PV technologies are deposited on the solar glass. And since the material consumption for the PV layers are so little, every time our discussion about the environmental impacts of PVs convert into a discussion about glass, production of glass. So they dominate all the environmental impacts, and they also dominate the cost of electricity in PV. That's why so newer studies on PV technologies are aiming removing the glass layer completely and then bringing some plastic materials that replace glasses. And one last research study that I wanted to talk just a little bit about this eco-efficiency concept. So we talk a little bit about the environmental impacts of PVs, but that cost is an important parameter too. So we wanted to merge these topics, environmental impact and cost, and bringing up this eco-efficiency concept a little bit. So the idea is reducing in both sides, cost and environmental side. And we know that there are several materials that could be used in each case, and we wanted to really find out those low cost and low impact materials. So that was the last study that I wanted to show here. So from life cycle carbon emissions perspective, so we identified that again polymer based absorbers and CNT and perovskite, these are the three absorber materials that have lower impacts compared to cadmium selenide quantum dots and CCTS types. From the contact material perspective, we have identified that aluminum FTO materials, these have very little CO2 impacts compared to the alternative. And from GWP global warming potential again perspective, the transport layer that contains tin oxide, copper iodine, these may work really well from environmental perspective. So we looked also their cost as well, and then again we identified the low cost materials at this point. So with that, I wanted to finalize the key research questions from my research. And I wanted to talk just a little bit about my current ongoing project. So this is an NSF SESYNC project funded energy water nexus analysis of solar energy industry. So we're gonna finalize this project within a month or two. I think February is the deadline. So our budget was about 90K. So the idea with this project basically bringing up researchers around the world to a table actually, and then merging the data that's coming from different perspectives. So energy and water data was merged in this study. So we have participants from University of Wisconsin-Platteville, Michigan State University, San Diego State University, Griffith and University of New South Wales from Australia. Again, we have a person from social science, Sandra Margaret Pratt from Michigan State University. We have also some industry collaborator. One is from China, sustainability. One from solar industry, Parkit Sinha. And we have two water person from industry, Chad and Ed. So that was a great paper. So we published one paper within this project, and then the second one is on the way. And especially we involved a lot of undergrad students in this research. So that was really good work. good collaboration with various collaborators around the world. And the second project that I wanted to mention is recently funded sustainable recycling of perovskite photovoltaic waste. So I'm the PI of this project, and this project is funded by Department of Energy. Our budget is around 200K here, but could be a little bit more than 200. So the idea is now we have that um, understanding to recycle the PV waste coming from perovskites. Um, so we wanted to remove the glass layer from perovskite PV cells without cracking the solar glass. So that's our idea. John Keller and Brett Carlson from Materials and Mining Engineering will be the co-principal investigator of this study. We also work with US manufacturers of advanced photovoltaics, and University of Toledo is a part of this project. We are very excited about this project, and we're gonna hire 2 grad students with this project and 2 undergrad students involved with the research. And this is another research activity from my team. We are waiting for this project idea. So the idea is integrating perovskite technology with solar flow battery system. So this idea brings University of Wisconsin Madison and University of Toledo and South Dakota University. Our university is the Mines, and I and Song Jin from UW Madison will be the principal investigators of this work. And actually, this will have a huge budget, so we are expecting a little bit more than 2 million for this research activity. And I wanted to finalize my slides. Just wanted to remind you some significant conclusion of our research. So I talk about this emerging PV technologies, and I ask about, are perovskite PVs more environmentally friendly than the commercial solar technologies? And the answer was yes, a lot more. And how are the use phase and mining related toxicities are comparable with other technologies? And we identified copper and lead could be some concerns, but not huge at all. And the other question was, will tandem cells have lower environmental impacts than 2 constituent single junction devices? And the answer was, again, having tandem structures would be a lot beneficial compared to single constituent PVs. So with that, I can finalize my presentation. And then I just wanted to open up the chat screen here to see if you have any questions.
Thank you, Doctor. Yes, if you have any questions for Dr. Seelig, please put them in the chat and I'll watch for them. Thought I had it up. Okay. Sometimes they're a quiet group.
By the way, I can't see the attendees here. I can only see you.
Oh,
so interesting. Yeah.
Yeah. They might, yeah, I'll give them a second. I'll watch. Sometimes. Yeah.
I especially wonder if we have any alumni attending this meeting, working in energy related industry here, especially in renewable energy.
Yeah.
I don't have too many contacts here. Great.
Yeah, if you work in renewable energy and would love to connect with Dr. Seelig, that would be great. Just think there might be, I have to look. Might be one or two.
Mhm.
Yeah, I'll have to look and see. I think. Oh, geez. Yeah. I know I asked about green hydrogen and now they're just falling out of the woodwork. So anyways, okay. Well, thank you all. If you do have any questions, please feel free to drop them in the chat. I'm going to put a survey in there. We're always looking for feedback and any ideas on webinars that you might like in the future. So please fill those. And then as we get going for 2022, because that's right around the corner, we have some fun, exciting talks. Industrial engineering is going to be given their department update on January 6th. And then the next digital lunch and learn will be, the topic is of climate change, and I'll have more information about what Dr. Capehart is going to be talking about then. But I will drop the links there for you. So if you'd like to register for those. And then if you know someone or have a senior, anyone that's interested in attending the School of Mines, admissions is giving a nightly talk about navigating the college search. So all those links are in there too. So I appreciate it.